organizing this nice meeting and also for inviting me to come and listen to the talks. Okay, so today I'm going to talk about some recent work that I did on driven integrable systems and their possible emergent steady states. And at the outset, I would like to acknowledge my collaborators. So Shourabh Nandi is my PhD student, and Deeptiman Sen is my colleague from Indian Institute of Science, Bangalore, and both of them are in the audience. And if you are interested, this is the archive reference for this work, and this will soon be published in Physical Review X. Okay, so let's see. So my job was made much easier by the previous two lectures of Stefan Keren, so that's nice. So, but still, this is the broad plan of the talk. So, unlike the previous two lectures there, we'll now concern ourselves with time-dependent Hamiltonians. So we'll again consider non-equilibrium steady states of driven many-body systems. And now there is a time-dependent Hamiltonian, and the Hamiltonian is being continually driven in time. So that's the difference from, let's say, the discussion in the last lecture. And again, there is no external heat bath attached to the system, so the dynamics is completely unitary. Okay, so first, I'll discuss about a certain class of integrable systems, and I'll also introduce a different geometric picture to understand some already existing results in the well-known periodically driven case. So the periodically driven case is, of course, when this function h of t is a periodic function of time, where this capital T is the time period. Okay, from then, I'll move on to what happens when you break this periodic structure in time. So you essentially concentrate on an h of t, which, let's say on an average, is still periodic in time. But if you look at it microscopically, if you look at the function, then it's no longer periodic, it's aperiodic, and there is no unit cell in time in which you can fit h of t. Okay, so that's why it's aperiodic. Okay, and then I'll actually discuss two particular examples for the sake of this talk. One example is when this aperiodic perturbation is some kind of a random noise in time. And another example is when this aperiodic perturbation is some kind of a scale invariant noise in time. And both of these would be, as I said, aperiodic functions. But we'll see that they'll have entirely different steady state properties. And then I'll conclude and just point out some future directions. Okay. Okay. So we heard about driven systems, and there's some specific calculation in the transverse field Ising model, where let's say you start the system at some initial state and you look at some local property. Let's say the X component of some spin at this particular site. And for simplicity, imagine that we are just doing a quench where the Hamiltonian has some initial value, and suddenly at time t equal to 0, it's changed to some post-quench Hamiltonian, and then it just stays like that. Then what one can show by just doing a exact calculation, that initially this sigma x varies in time, but then as you can clearly see from this figure, it seems to be going to a steady state. Of course, if you zoom in here, there are still oscillations, but if you take the thermodynamic limit, you can show that these oscillations keep on becoming smaller and smaller, okay? And this value, this final steady state, can be calculated from the so-called generalized Gibbs ensemble formalism that we heard about, okay? So there has been lots of progress in understanding this kind of a system for at least certain classes of integrable models. And there's another kind of time dependence in the Hamiltonian that one can imagine, which is that the Hamiltonian is continually driven in time. So here, once you reach the final Hamiltonian, you just stay there, right? You don't change it as a function of time after that. But of course, you can imagine functions where the time dependence always remains. And one simple class of functions, which is also very important for other reasons, is periodically driven systems. So the Hamiltonian satisfies this equation in time. Okay. Again, for these periodically driven systems, one can give a steady state description which is sort of analogous to what we heard for the case of the quench. But here the steady state only appears if you look at the system stroboscopically in time. So what it means is you look at the system as a function of this n. So n equal to 0, 1, 2, and so on. So your time interval is separated by the microscopic time period of the driving Hamiltonian. So that's why this is called stroboscopic time. Okay. So if you look at this periodically driven problem, then one can actually convince oneself using similar methods that you again reach a steady state. Okay, so the important quantities. So what are the guiding principles that you have here? The guiding principles are the conserved quantities during the dynamics. So of course, if I just do a quench, then the only conserved quantity, at least for a generic system, is the final Hamiltonian's expectation value. And then if we write a maximum entropy description which is consistent with this only conservation law, we basically get the e to the minus beta h density matrix, right? So this is how we usually formulate statistical mechanics as well. Okay. And the important thing to stress here is that even though the state is pure at all times, because there's no external heat path attached, remarkably the local properties of the resulting pure state at late times is indistinguishable from this maximum entropy result in the thermodynamic limit. Okay? So this is something which was also stressed in the pedagogical lectures. Okay, and of course I don't need to go through this because this was the last thing discussed, so this should be fresh in your memory. So at least for generic systems, we can sort of understand this thermalization as a consequence of this eigenstate thermalization hypothesis. Okay? And this was discussed in the last talk, how this will come about. Okay, right. Yeah.
About the last talk, can you emphasize this again? Because you're saying high energy again. So
oh yeah, but actually those are again things which there are no very precise answers, so maybe we can discuss after this talk, right? Essentially, I'll say the same things as he said, right? So there's nothing more useful.
all right.
And the other things we can discuss in private. So, okay. Okay, right. So let me first focus on periodically driven systems, and let me first look at how to describe them. Okay, so as I already said, in periodically driven systems, if you look at stroboscopic time, so time separated by capital T, then at late times there is synchronization of the local properties with whatever drive frequency you have. So 1 over T basically defines your drive frequency, right? Okay, and because of that, you can define a periodic ensemble to describe those properties. Okay, and the interest in the field is also because it can actually stabilize, these kind of drivings can actually stabilize non-equilibrium steady states which have no analogs in equilibrium physics, right? For example, there are these things called Floquet time crystals, and one can show that you cannot have these things in any equilibrium situation. So that's very interesting, even at a conceptual level. Okay, so I'll say in one line. Okay, so there are these many-body localized states which are interacting versions of Anderson localized states. So in certain parameter space, it can happen that if you drive the system at a certain frequency, you actually get local response at, let's say, half the frequency. And this number half is a stable number. So it doesn't change if you change your parameters by a bit. So it's a well-defined state in that sense. And that's correct. It happens even there. It happens even there. This is not like the first instance of this happening. Indeed, it happens even there. That's right. Okay. Right. Okay, so the way you can understand these Floquet systems or periodically driven systems is the following. Since we are right now concerned with the dynamics after stroboscopic times. So then the basic object for me to look at is the unitary evolution operator after one time period. And let's say I want to find the state of the system after n time periods, I just need to apply this unitary matrix n number of times, right? So that's the basic object to look at. Okay, so this is a unitary matrix, so this can always be expressed like this. This is not a deep statement, and where this HF is a Hermitian operator. So this UT is called the Floquet operator in literature, and this HF is called the Floquet-Hamiltonian. Okay, so, this is what I had already said, that when n tends to infinity, there may be a steady state description here. So, it has been shown, at least numerically, there are reasonable evidences that generic non-integrable systems, when you keep on driving them periodically in time, they heat up to an infinite temperature ensemble. So the beta that we heard about there, that beta goes to 0. Okay, right. However, this is not true for certain other systems like many-body localized systems, and more importantly for this talk, for integrable models. Or actually, I should add a qualifier for certain integrable models, because we don't know what happens for beta integrable models, whether they heat up to infinite temperature or not. Oh, that's right. So, yeah, that's right. Correct. So yeah, okay, thanks for that question. So it happens that if you take a non-integrable model, irrespective of the other details of that system, the beta is always 0 for that system. So there's a reason. Okay, so that's the answer. No, I mean, even integrable models have steady state descriptions. It's just that non-integrable models, you need only one parameter to describe the thing, that's beta, and that beta happens to be infinite temperature. So the beta goes to 0. Yeah, that's basically because this Floquet-Hamiltonian, if you look at the eigenstates of this Hamiltonian, that seems to all cluster around infinite temperature if you look at local properties. That's one way of stating it, yeah. Oh, no. Right now I'm just considering periodic functions in time. Oh, that's correct. So, I mean, they can be like rational multiples of each other. As long as you can define a unit cell in time to block the drive, it's okay. I mean, it can be one frequency, it could be more than one if they're multiples of each other and so on. See, if you take two frequencies which are like irrational of each other, some omega 1 and omega 2, then you cannot form a time period per se, right? You cannot fit it in any unit cell in time, that's all. So for things which you can fit in a unit cell, they're periodic functions by definition. That's it. Which temperature part? Oh, the infinite temperature. Yeah. So as long as your drive is periodic, there are at least reasonable numerical studies which seem to point to this thing. Yeah. There's no proof as such. Right. So the kick rotor system has two regimes. It has a chaotic regime and it has a non-chaotic regime. If you go to the chaotic regime, the energy seems to grow in an unbounded fashion. So this is similar to what's written here.
I didn't want to pick that on the kick rotor. I just mentioned a classical setting.
Yeah, so the short answer is this thing should also happen in a generic classical situation, which does not have extra integrals of motion. But again, there's no hard proof for this statement, but that's the expectation. Yeah. Okay, good. So let's focus on certain precise models because, of course, these questions are very grand. So you should just focus on some models first to understand them. So the class of integrable models that I would discuss, so this was already introduced in the previous talk and even by other speakers. So this is the transverse field Ising model. So for example, you can see that there is a magnetic field in the transverse direction. So let's call X as the transverse direction. So you can make the magnetic field time dependent for the purpose of this talk, okay? You can also do something similar in 2 dimensions by using the Kitaev model, and then you can perhaps make any of these couplings to be time dependent. So the nice thing about these models and some other models like this is you can map all of these to free fermions by using something called the Jordan-Wigner transformation. Okay, so for the purpose of dynamics, where this Hamiltonian is a time-dependent object, not some static Hamiltonian, I actually would prefer to go to a new language of this pseudospin representation. I just think it's much more intuitive to think in this language. So what is that? So as I said, the system can be written in terms of free fermions by doing Jordan-Wigner transformation. So you'll end up, let's say for concreteness, I just look at the 1D transverse realizing model throughout the rest of the talk. So then the system the Hamiltonian can be written like this. There are some hopping terms and there are some pairing terms, right? That's the Hamiltonian. Okay, so then of course if you see Hamiltonian like this, you will go to momentum space and then K is a good quantum number, so the problem will just break up into much smaller blocks. Okay, so then you can convince yourself that you can just go to a pseudo-spin half representation where I added the word pseudo-spin here because this is different from the original spin, where you can define the spin up state as this and the spin down state as that, where this vacuum of fermions in terms of the original spins is just all sigma x being +1. Okay, so that's the vacuum of the fermions. So if I think like that, then the whole wave function can just be expressed as the tensor product of wave functions at each k, and at each k you just have a spinor wave function. Okay, so this is some like for any spin half, this is the general state that you can write down, and you can just tensor product that. So that's the pseudo spin representation. And of course, if your system size has capital L sites, then there's some quantization of these momenta, right? And yeah, okay, these are the details, but there'll be some structure like that. Okay, now the important thing is, because this G is a function of time, and now it doesn't even matter what function of time it is, I can just understand this dynamics and the state of the system completely by knowing what is this UK of t and VK of t at each k, right? If I know it at each k, then I have the full wave function and I can calculate anything. So then, at each k, the problem just reduces to a spin half problem in a time-dependent magnetic field. So the time dependence comes because this G of t is a time-dependent function. So that's it. So you can see that there's some Z component of this magnetic field and there's some X component of this magnetic field. And so at each k, there is an individual Bloch sphere, right? And it's doing something which just depends on its own time-dependent magnetic field, right? Okay, so that's the setup. And you just study this problem. Okay. So then, the nice thing about these kind of models is that if I want to focus on local properties, exactly like was defined in the previous lecture, then the fundamental object to look at is the reduced density matrix of that subsystem, where, of course, I should emphasize that suppose the number of sites in this subsystem is small l, I'm always working in the limit where small l is much, much smaller than capital L. Okay, that's very important. So that's very important for the rest of what's going to follow. So if I want to write down the reduced density matrix for this subsystem, then because the original system is integrable and breaks up into free fermions, it was actually shown by Peschel and even people after him, but he proposed the idea first, that you basically just need the knowledge of two L cross L matrices, small l cross small l matrices. This is very different from a generic situation. In a generic situation, you'll need some exponential L cross exponential L information to construct the reduced density matrix. And the simplification happens because these are free fermions, okay? So, so basically, these I's and J's are now restricted through this subsystem. The I's and J's cannot live outside the subsystem, okay? Then you need one matrix which is this, just Ci dagger Cj, right? And this is of course a function of time because this, you can express it in this UK, and this is a function of time. And there's this Fij. So basically these are the most simple 2-point correlations you can think of in terms of the fermions. So once you have these two L cross L matrices, you can construct this 2L cross 2L matrix, And if you know the eigenvectors and the eigenvalues of this matrix, you can construct the reduced density matrix. Okay, so basic point is that these are the fundamental objects, right? And okay. Oh, this n is the stroboscopic index, n equal to 0, 1, 2, because for at least this problem, I'm looking at it stroboscopically in time, right? Exactly. So it's discrete intervals that I'm looking at. But of course, you can write t as well there, doesn't matter. This definition is correct. Okay. Good. So now I try to motivate this geometric picture, which I'll come to. So see, now we are interested in local quantities only, right? So it turns out that I don't need to know these UKs and VKs in detail at each momentum k. There are some coarse-grained objects that I can define in momentum space, which have much better properties in time. Okay, so so basically in k-space you have lots of momenta, right? And the spacing between two momenta is of order 1 by capital L. Now suppose you are concerned about local properties in a patch of size small l. Then you can actually show that you can adopt a coarse-graining procedure in momentum space like this, where I have bunched up consecutive k modes in these little boxes. So as long as the size of this box is much smaller than, as long as the size of this box is much larger than 1 by capital L and much smaller than 1 by small l, you can just define these coarse-grained objects here, which are just the average over all these momenta, right? You can just see that here. And these completely determine the local properties in that patch of small l. Okay? So basically, this is just breaking the original sum in k into two parts like this. That's it. And then you sum up one thing, and you also realize that this cos k I minus j and sin k I minus j can be replaced by something like this, where this kc is just the average of the momenta in these in this cell, for example, and I minus j, importantly, one should remember, is bounded between 0 and small l. Then you can just show that this is true. Okay, so this object has actually nicer properties compared to the same objects at single k modes. For example, if you drive the system periodically, and let's say I start from one particular initial state, so let's say the initial state is all spins being polarized in the x direction at time t equal to 0. And for the rest of the talk also, that'll be my initial state. Then you can easily show that this, for example, this UK square, it doesn't have a smooth end tending to infinity limit, because this basically just does some Rabi oscillation. And that's very easy to show. Why? Because you see, in it, unlike this figure where there is only 1, 2, 3, 4, 5, 6, but it's not 6, it's actually a large number of momenta in each cell. Then you can even take, so you can even take all those n points on a unit sphere. So all of those n points on a unit sphere, and then there's a unit sphere which represents your coarse-grained momentum cell, and there are capital NC points, where NC is the number of momenta in your cell. And then because this NC is large, you can even define the probability distribution of these points as a function of time, right? So one statement which one can sort of show immediately is, if the system were to go to infinite temperature ensemble in a local sense, then this probability distribution when n tends to infinity would have gone to a flat function, because it's infinite temperature. But you can compute this function here for a perfectly periodic drive, and you can see that this is the analytic function, by the way, and this is the function after a certain number of large drives. Okay, you can see that this is clearly not a flat function, and that's another way of understanding that the system does not go to infinite temperature because of the conserved quantities that one has in the dynamics. Okay. Oh, that one can just understand geometrically. So basically, it's just some pattern like this on the Bloch sphere. It's a perfect circle, right? Because, yeah, that's it. So it's bounded and then it's 0. Yeah. Okay, so somehow it's magically working again. So that was the story in this kind of a geometric framework about these periodically driven systems. Now I have to rush a bit. So now we go to this perturbed Floquet dynamics. So now imagine for simplicity that our periodic drive in time is just a pulse. So there are repeated pulses and each pulse has a width of capital T. So that's a periodic function in time. So then you can just construct a non-periodic function in time by following that recipe. So you could just say that some pulses are widened by an amount dt and some pulses are shrunk by an amount dt, right? And of course, for simplicity, I'm just choosing a two-step kind of a process, t plus dt and t minus dt, so that I can just work with some discrete sequences. So clearly there are many ways of cooking up non-periodic functions in time like that, right? And then we ask, what are the steady states of this? So on a mathematical level, the problem now becomes the following. At each k, you have a t plus tau 1 dt and t plus tau 2 dt and so on, where the sequence tau 1, tau 2, tau 3 is +1 or -1. And of course, depending on what physical situation you have, like what kind of perturbations in the periodic time structure you want to give, you'll choose different kinds of sequences, right? Okay, and of course, if dt turns to be 0, then you're back to the original case. Okay, so now, what is the case when the problem is perturbed with random noise? That case is simply where this sequence tau I is any typical realization of a random process where you just flip a coin and assign a +1 or a -1, right? So that's a perfectly random noise, if you wish, has no internal structure. Okay. However, you can imagine many other sequences which are neither random nor periodic. Maybe they are quasi-periodic. And then there is some internal structure present, even though that structure cannot be represented periodically in time. So I'll just show you results from one such example. And that sequence is actually called the Thue-Morse sequence in mathematics. And it's a very well-known sequence in mathematics, but we'll come to that soon. Okay, so I'll unfortunately have to quicken my pace now, but I'll be happy to take questions later. So now, suppose you put on a small dt, and now we are considering this random noise case. Now let's look at these probability distributions on any Bloch sphere in momentum space, okay? Now you should see that now we have two kinds of objects, uk t minus dt and uk t plus dt, right? And again, I can show that these can always be written like that because these are just SU2 matrices. Okay, where this direction alpha k, this direction ak and this direction bk are only slightly different from this unit vector ek, right? Because dt is a small number. Furthermore, one can show that this difference is just order dt times sine k, where k is the momentum of your coarse-grained cell. Okay, so then if one thinks in a random walk sense, then the appropriate control parameter turns out to be square n times dt times sine k, and this is square root n and not n because there's a random walker. And then essentially you can see that what happens in this unit sphere. So, or for example, in this probability density. So you see, when you leave the system initially with this unitary dynamics, it seems that the probability distribution on each coarse-grained momentum cell approaches the answer for the perfectly periodic case. That's this dotted line. So when n is equal to 100, the probability distribution actually seems to approach this. However, if you wait long enough, let's say n is 10 to the power 4, there are strong deviations. If you wait even longer, you can see that this is going to a flat function, right? And you can just see it pictorially here also. These are the locations of these NC points on the unit sphere under the dynamics. So you can clearly see that this is going to infinite temperature. Okay, and of course this model is still integrable. You haven't lifted the integrability, but because you have broken this periodic structure in time, it seems to flow towards this infinite temperature ensemble. And okay, without going into details, you can also show that how it goes to infinite temperature. So, okay, in view of time, let me just show you the result. So basically, the system, suppose dt is very small, then there is a pre-thermalization regime, and the time the system spends in this pre-thermalized regime is 1 by dt whole square. So when dt is very small, this time can be quite large. So within that time scale, you would think that the system is actually approaching the periodic Gibbs, generalized Gibbs ensemble. Okay. However, if you wait longer enough, the system realizes that it needs to go to infinite temperature. Okay. And this is basically just some distance measure which tells you how far you are in terms of the reduced density matrix being distinct from identity. Because if it's infinite temperature, the reduced density matrix should be identity, right? So you can see that there is a particular way this will fall off, and one can also predict how this thing will fall off. It'll basically fall off as n to the minus half, and the way it approaches this generalized Gibbs ensemble in the pre-thermal regime is also interesting. You can also work out the corresponding power loss there. Okay, good. So this is the story for noise, like an aperiodic function, which is built up from a periodic function plus random noise in time. Okay. Now we actually come to the case of the scale invariant noise. So now I need to take this sequence not to be a random sequence. So this is now some sequence called the Thumor sequence. So let's just study what this sequence is. So there's a recursive construction for this. Let's see the first element, tau1 of the sequence is -1. Then I go to the next level, then I just look at this -1 and the next element is just the complement of that. So that's +1. Then I go to the next level, so I already have -1 and +1, so that's this entire thing, and I complement this entire thing. So that's +1 and -1. Right? Then you go to the next level, this -1, +1, +1, -1, and you just complement this entire block, and that's what you get. So I hope this recursive building up of the sequence is clear. So clearly this is an infinite sequence, right? You can just build it up like that. Right. Now, also in this recursive construction, at each level m, you obtain the first 2 to the power m elements of this sequence. Now, what you can easily verify is that this sequence has a self-similar structure in time. So how do I verify that? I take the infinite sequence. You can see that it's infinite because the elements are spilling out of the slide. Okay, so it's clearly infinite. So then, let's say you remove the. Okay, let's say you remove all the sort of even terms from this sequence, all the even terms. So this guy, that guy, and so on. You go back to the same original sequence. So clearly it's self-similar in time. And clearly it's not a periodic function. So because you cannot put this sequence in any sort of a unit cell in time. There is no finite block here which is repeating itself, right? So clearly this is not a periodic sequence and this is not a random sequence. So this is a quasi-periodic sequence. Okay, so now let's say we look at these coarse-grained quantities again as a function of n, right, when dt is small. Now I'm just showing here the behavior for 2 different coarse-grained momenta. So this Kc just represents their corresponding averages. Now you can clearly see that there is some rather complicated behavior here, unlike in the periodic case, where it just went to some finite value very quickly. And it's not even clear from this picture that there is an n tending to infinity limit. It's not at all clear from this, right? So then the question is there a well-defined non-equilibrium steady state? Okay, so, right. So the answer is yes. So let's see how we can do that. So, okay, so I'll do some abuse of notation here. So I'll flip notations. Now this ukt minus dt is a naught, and this ukt plus dt is b naught. Okay. Now, let's say there's some initial state, and of course I should do this at each k to find the full wave function. This is the original Thue-Morse sequence acting here, right? Now I define some recursive relations. So from these original 2x2 matrices, I can construct some matrices A1 and B1, where A1 is just B0 times A0, and B1 is some A0 times B0, right? So then you can write this entire thing in terms of these A1s and B1s, right? Then you can just carry this out further, and you can just do this, you can just do this, and then you see this. So here n is equal to 16, right? Because there's 16 unitary matrices, and you can express everything in terms of just one single matrix A4. That's why we adopted this structure. So basically there's a scale invariant structure in time, and these recursive ways of writing that just utilize that, okay? So now there's a very interesting thing. Okay, so the first statement is the evolution operator after exactly 2 to the m drives is given by AM. I hope this is clear from this simple example, right? So here this is A4, and 2 to the power 4 is 16, right? Okay. Now comes the remarkable property. One can show, and I'll have no time to show it, one can show that there is a very peculiar fixed point properties of strings of SU2 matrices, through which you can show that if this index M is large enough, then AM tends to BM, no matter what the original A0 and B0 are, okay? And then you can see that there's an emergent time periodicity. And how is that? Because just imagine that you're actually doing a lot of coarse graining. Let's say you have reached A200, right? Somewhere down here. Then A200 is the same as B200, which is the same as A200. So now you're back to a periodic structure in time. But this is clearly emergent. It's not present microscopically. I really do not have time to discuss how this happens because I can see the time here. But if anybody's interested, I can explain it. So this you can see pictorially very nicely as well. So now again, you consider the block sphere, right? And let's say I focus on one momentum cell. That momentum cell has a very large number of individual momenta there. It just shows the motion of all those. So now look at the time. Clearly, as I said earlier, the time is running as 2 to the something, right? So you're looking at really late time properties here. I mean, 2 to the 5,000 is an astronomical number, and you don't need to worry about units of time then, right? Okay. But okay, let's see what's happening here. See, if there's a time periodicity, we expect a perfect circle like this, right? This is what I already told you. Now see, the original motion is extremely complicated. Even here it's very complicated, but even here at 2 to the 20, you can sort of see an attractor building up, right? This guy. Now when you go to even later times, it's even more clear. And then you go to very late times and the motion is on a perfect circle. That's because of this emergent periodicity, time periodicity. And that allows us to actually show that there are some emergent conservation laws in this problem, right? And I can explain the construction to anybody who's interested. So the basic idea is because there are these emergent conservation laws, the system does not go to infinite temperature in this case. But what is more important is because we have identified these things, we can construct the corresponding generalized Gibbs ensemble here. And we choose to call that a geometric generalized Gibbs ensemble. The reason is very simple. We are looking logarithmically in time. That's why it's a geometric generalized Gibbs ensemble, right? So you can see what's happening here. So I have just calculated some local quantity and I have just used this thing to calculate its steady state values at 2 different values of dt. By the way, you should notice that for this story, it's not even necessary that dt is a small number compared to the original t. dt can be even larger than this and everything I'm saying goes through. Then you can see that on some extremely long time scale, the system does relax to its steady state. The steady state that I predicted in the previous slide. However, if you look at this for some short time interval, see, even though this is not short, this is already 1 followed by 1, 2, 3, 4, 5. 5 zeros, right? You can see that this is the steady state value, but the system is not showing any tendency to go to it. And you should just just to see how surprising this is, you should just go to the perfectly periodic problem where dt is 0. And you can see that very quickly, even for n equal to 100, the system, the local property has approached reasonably close to the steady state, right? But here it's much more complicated, and probably this is a generic feature of other quasi-periodic drives as well. I don't know. Okay, so conclude. Basically, non-equilibrium steady states of continually driven systems is not understood in general. So here we have just constructed 2 examples of driving protocols where there is no periodic structure in time. For one such structure, we show that the steady state is an infinite temperature ensemble with some interesting pre-thermalization behavior. For the other, we see that there are some emergent conservation laws at extremely late times, and that leads to this new geometric generalized Gibbs ensemble. And basically, it seems that there is a way of generalizing this thing further to integrable models, and that's what we are currently thinking about. And so I'd like to end here, and I'd like to acknowledge very useful discussions with my colleagues in different institutes, and I'll also like to thank you for your attention. Thank you.
Nice talk, Albert. When you talk about the steady state in the first part, where you didn't have any noise on, you have this steady state which is
periodic, for the periodic.
So it's a steady state on average over a period of time, or it's average over a period of time of
No. Oh, well, you strictly don't need to average over it if you're in the thermodynamic limit. Then what you do is, suppose there's any local observable O, right? And I'm just looking at particular times, let's say 0, capital T, capital 2T, 3T, and so on, right? Then initially maybe there is some complicated, okay, sorry, I'm just looking here, so I should just draw points. Maybe there is some behavior like this, but at late times there's a well-defined value at which this sequence of points converges. That's what I mean. Right? So this sequence of points converge to some well-defined value at late times when n tends to infinity. Right.
But your system is still finite.
No.
But L also tends to.
L is very large. Okay. So you're always working in the limit. And you also want L to be. Right. Yeah, I think I stated that, but maybe I didn't stress it enough. Yeah, so this is very important. Okay. Otherwise, there are various issues. And
yeah, I was thinking about recurrence time scale
exactly.
and all that for me. Okay, thanks.
So in the case with the random dt, was there a critical dt above which you went to infinite?
No. There's no critical. So this dt can be as small as you want. Suppose dt is extremely small, then this pre-thermal regime is very large in time. It's because it's 1 by dt whole square, right? So even for very small dt, eventually you'll go to infinite temperature. So there's a scaling, yeah.
So in these random time step cases, if you average over the random noise, what happens? Do you still have?
I think you will have something very similar, because I showed that the typical realization shows this property. So if typical realization of a random process shows this property. So clearly, this is a property which would remain on averaging as well.
Does it sort of converge faster? For example,
no, it won't. It'll just converge like that. See, one reason I stressed on the fact that this is a typical realization of a random process is because it's a unitary process. If you average over all possible noises, then that's not strictly a unitary process. This is a unitary process.
Your methods rely heavily on the fact that the models map to free fermions,
exactly.
Right?
So to the 2x2 structure.
To the 2x2 structure. Yeah. Is there any literature on like driven XXZ spin chain, or I mean other integrable spin chains where they see some similar?
Well, firstly,
behavior?
I don't think people have explored these quasi-periodic sequences too much even here.
No, I just mean periodic driving, just single frequency driving of XXZ spin chain.
So. Yeah, I'm not completely sure. No, that's correct. But I think he's not asking about the time crystal. So your question is, do people know what is the steady state description for an XXZ chain, for example?
I mean, my question is the fact that if you have a single frequency drive, let's forget the multiple frequency. If you have a single frequency drive, the fact that the integrable models do not heat up into infinite temperature seems to be known for models which map to free fermions. How generic is this?
So I'm not exactly sure whether people know this for sure for the XXZ model. I think it's still not understood whether it heats up to infinite temperature or to finite temperature if you drive it periodically. But I'm not sure. Somebody might correct me on that. This is my impression.
So if you, with random noise, you got thermalization, and then...
I won't call it thermalization.
I mean, like,
it just flows to infinite temperature, right?
But with this sort of correlated noise, you get this...
weird state.
So, I mean, I guess if you're like... I mean, what is the correlation function of this noise? I mean, and like... typically,
I see.
Yeah.
You mean the Fourier spectrum, right? So basically you won't get quote unquote any Bragg peaks here because there's no periodicity in time, right? So let's say I just take that sequence and Fourier transform it. That's your question. That's one way of thinking.
Time.
So it's a self-similar function in time. It's a scale invariant function in time. It's scale invariant in time.
But it decays as like at large. Like if it decays kind of fast, then I would expect it should be the same as uncorrelated noise.
But it's not. We saw that.
Is it like a power law decay?
I don't remember off the top of my head. I need to look at the Fourier transforms. I don't remember off the top of my head.
A disorder in time axis.
Yeah.
Okay.
Yeah, some quasi-crystalline time axis, if you wish.
You know, because you know, there's with Anderson localization, all these things.
Right.
When people put correlated disorder, it behaviors completely change from just uncorrelated disorder.
Right, but
because you start to see even in 1D metal insulated transition.
Right. But there's an important thing here. I mean, for this sequence, and I haven't shown you other kinds of sequences of quasi-periodic thing. You see, the correlation is built up at all I shouldn't say length scale, time scales, right? See, if the correlation is just restricted to a finite interval in time, you can just coarse grain in time and then it again goes back to the random noise case. That won't be very different. Yeah.
Okay, so one more question about the spatial prescription. Does it work for bosonic system?
Yes, it does.
So you can calculate entanglement entropy?
You can. It's just a bit harder, but you can. So the main idea is the following. It's very simple to state physically. Even for free bosons, Wick's theorem is satisfied. So suppose you have a subsystem, as long as you can write a reduced density matrix which gives the 2-point correlations correctly, you're done for higher point correlations. That's it. That's the main idea.
You can calculate even time evolution in entropy using the spatial envelope.
Yeah. It's a bit harder, but you can do it. Yeah, it's not. Yeah.
How do your results compare with if you try a bunch of incommensurate frequencies?
That analysis is much harder, right? Because see, here you have discrete sequences, so you can still do some things mathematically. Now, suppose you add up two sine functions which have incommensurate frequencies. We don't know how to mathematically address that yet. The hope is some of this will also remain there. But I cannot give you a very straightforward yes or no answer right now. But that's obviously a much harder problem to deal with mathematically. This is a simpler way of posing the problem.
So that's why you chose.
Exactly. That's why we chose discrete sequences.